So a lot of what we're going to talk about in this lesson 1 has to do with how science works. First, the basic idea of how we build scientific knowledge. We're not going to spend that long on that. And then we'll talk a little bit about how to do the math that we need in this course. Of course, you'll have a calculator, but if you know how to multiply numbers with one digit, like your multiplication tables from way back when, and you know how to add numbers of one digit or two digits, you could probably do all the math a lot faster without a calculator, believe it or not. Okay? But we'll go through that. So the basic idea, or the basic idea of how we build knowledge, is in science we are willing to accept that what we call knowledge is actually not true. So we're always trying to improve on what we know. And there's different ways to justify knowledge or a belief. And there's ways that are different from these. But these are the ones that really have to do with science. People believe all sorts of things, and those aren't scientific beliefs necessarily. And you could think about what you might believe in and how you justify it. It could be just as simple as, well, my ancestors believed that, so I'm going to believe it. But for science, we have some specific ideas that we'll talk about. So one that we'll talk about a lot is the scientific method, and we'll expand on that a bit later today. There's something called Occam's razor. So does anyone know what Occam's razor is, or someone who took the course before? So what is Occam's razor?
The simplest answer is usually the right one. Like you cut out all the details and find the simplest answer.
So that's, now why would that be a good thing to do or not? Sometimes the answers aren't simple. Sometimes the answers are only simple if you look at them in a certain way, right? So a lot of people are like, we'll learn about general relativity, and people might argue, well, general relativity, there's so much going on, and it's so much more complicated than Newton's idea of gravity, but that's just because you're looking at it in the wrong way. If you look at it a different way, general relativity is the simplest possible theory of gravity, believe it or not. And the point is sometimes what seems simple or complex is just because we're looking at it in the wrong way. In a certain sense, our current theory of particle physics and all this complexity of chemistry and all that comes from a theory that is almost as simple as possible. You know, it's like, let's think of a bunch of theories. What are the simplest ones we can come up with? We'll module them all together, and lo and behold, that explains a whole lot. Now, from someone in your everyday experience, it would seem very complicated, but why does the theory of the universe actually have to do with our everyday experience in a certain sense? We've been stuck here. We're basically apes on a ball of rock near a middling star. Our everyday experience doesn't have to be the best way of looking at everything. Okay, the next one's called empiricism, which means that we observe things. We are empirical. We're looking at phenomenon and trying to explain those phenomenon and predict new phenomenon. So that empiricism is very connected with the scientific method, which is observe, explain, predict. Pragmatism, that means if it works, it's probably good. And that has to do with the predictions, right? So when science went from just being explanations to predictions, that's when it became really valuable. And that's when the scientific revolution happened and why we have this modern world of technology. was the realization, in part by Galileo. So Galileo, of course, he was an astronomer, but he was also pragmatic. He did calculations of the trajectories of things thrown through the air. So why would you worry about that? Before Galileo, people actually thought when something was thrown through the air, it did sort of like Wile E. Coyote running off a cliff. Have you ever seen that? So Wile E. Coyote, he runs off the cliff, and when his forward motion is exhausted by friction, only then he starts to fall. If you've seen that. So people thought like you would throw something and it would go up like this, and it would slow down in this direction, in the horizontal direction. Eventually it would go like that, and then it would fall straight down. Galileo was like, no, that doesn't make sense. There's something pulling it down at a constant rate, that's gravity, and he calculated that it would follow a trajectory like a parabola. Now, why didn't people realize this? Like you get out a garden hose and spray it in the air, and it makes this lovely curve, the parabola. But they just thought, they had this belief coming from Aristotle that things, when they were in motion, they had the basic state of something was not to be moving. So they had this belief that it would just exhaust its motion and then just drop. Now, why does that have to do with pragmatism? Because, of course, Galileo made tables of how things go. And what is that useful for? Well, Galileo was in Florence, and Florence is near a city called Pisa. And apparently, for centuries, everyone hates people in Pisa. It's true. Even now, people don't like the Pisans. And the Florentines and the Pisans were always having wars. So Galileo's knowledge, this pragmatic knowledge of using the scientific method and predicting, was very useful for like launching cannonballs at the Pisans. So despite the fact that he went against the church, despite the fact that, he was buddies with the Pope, but then the Pope locked him up, he never got killed, right? Other people were killed for saying that the Earth is going around the sun. He was just locked up in a lovely villa on the top of a mountain, of a hill in Florence. In fact, he was also, before that, he was locked up with the Bishop of Siena, who was his buddy. And the Bishop of Siena, of course, Galileo was well known around Europe at the time. So the Bishop of Siena really liked this because all these people would come to visit him to see Galileo. And this was Galileo being punished, living in a bishop's palace under house arrest, and having people from all over Europe come and visit him. So, of course, the Pope got wind of this and sent him back to Arcetri, which was good for Galileo because his daughter was a cloistered nun in a convent in Arcetri. So he was closer to his daughter, but he couldn't get all the visitors from around Europe. But the point is, since his science was pragmatic, it wasn't just astronomy, although the astronomical stuff that he discovered was actually quite useful. I think we'll hopefully do an exercise a bit later next week of one of the useful things that he discovered that was astronomical. Science is useful, and that's what pragmatism means. And if something doesn't successfully predict phenomenon, maybe it's wrong, but we know it's not useful. Okay? The last one is probability, right? So a lot of science, when we measure something, or at a basic level, the predictions of physics are actually probabilistic in quantum mechanics. But at a more empirical level, when we measure something, we don't always measure it correctly, right? There's some error in what we measure versus the reality. And we have to understand how those correspond, and whether, if we're measuring something different from what we expect, is it because we've made an error with our apparatus, or are we having to change our theory. So a great example of thinking about that was in the late 19th century, people realized that the orbit of Mercury wasn't correct according to Newton's theories. And they had subtracted out all the terms that they could think about from Newtonian physics, and they were left with a little bit more. And they knew that their accuracy was sufficient to measure this excess bit, that it wasn't that they were making a mistake, but you'd have to think about that. And that ushered in, that excess bit was predicted or explained by general relativity. So astronomy has all of these things mixed into it, and we'll think about all of them. And really, that whole idea, those ideas really started with Galileo, who in a sense is the first modern scientist, I would argue. Okay, so the ground rules. What are we working with today? So I talked a little bit about the scientific method, then we're going to jump into some math, and we're almost going to realize immediately that we end up, when we do astronomy, we end up with really big numbers. And we'll do a little experiment in class, I think, that will measure something, and we'll end up getting a really big number. So we'll have to understand how to deal with big numbers, and I'm going to spend a lot of time going through how we use scientific notation. And the next thing I'll talk about is measuring angles. So we're stuck on the surface of the Earth, right, more or less. So to measure distances, we can't take a yardstick and run it out to a star. But there's other things we can do. We can measure distances like a surveyor measures distances on Earth. So if a surveyor wants to measure the distance between here and the end of the block, the surveyor doesn't lay out a tape, usually. What the surveyor does has an instrument that can measure angles very accurately, and by measuring those angles can figure out these distances. So next week's tutorial, you guys will measure the height of that tower over there. It's not in the back of the room, but it's the one with the clock over there. But you won't climb up it, I hope. I hope no one will climb up it and drop a tape. That's not how you're supposed to measure the height of the tower. But you'll measure it by measuring angles, which is how we do measurements of distances in astronomy. And we'll talk a bit about the different units of distance as well before we get into some physics. So what is science? So I've argued that science has to do with knowledge, and this particular science here, it's from Wikipedia, and it is a little bit like some people might talk about social science, which is actually excluded from this definition, and maybe that's not fair. Although we are humans, we're social, and we are part of the natural world in a sense, I think. But some people might argue that we're separate from that. But the basic idea is that we're trying to build knowledge, and we make explanations and predictions about the natural world. So not only are we taking observations, but we try to explain those observations, but those explanations should predict something new, right? That's the important part. And that last step of predicting new things makes it very pragmatic, very useful, because I know if I throw the ball or shoot that cannon in this way, it's going to land where I want it to on those Pisans' heads. Lots of nasty things have been done by Pisans and to Pisans, but we won't. I can tell you stories about that. So the scientific method has a way of building knowledge. Science has a way of building knowledge. The first step is observations. The second step is explanation. And the third step is prediction. And then you loop back. Did your prediction agree with your new observations. So in astronomy, we make observations with telescopes. For the most part, although recently we have other sorts of instruments that we use to make observations. So on the left is a telescope in New Mexico that was used for the Sloan Digital Sky Survey. It's a telescope on the ground. It measures radiation from the sky, essentially the same radiation that we can see, the same range of wavelengths as what we can see. On the right is the Chandra X-ray telescope. It was brought up into not even near Earth orbit. It was brought up by the space shuttle. It's about the size of a school bus, more or less. So it's pretty big. And it's in orbit around the Earth where it goes out maybe a third of the way to the moon and comes back again. So it's really far out. The advantage of that is, well, first of all, it's above the Earth's atmosphere, it can measure X-rays. But the other advantage is it spends a lot of time away from the magnetic field of the Earth, so it can observe for a very long time the same point in space. So if we want to observe radiation from space, electromagnetic radiation, and you might not know what this means, but of course we'll get into that. That's not what we can see with our eye and not radio waves. We have to launch that into space, right? Because the Earth's atmosphere absorbs. But we have other sorts of observatories now that don't even look like observatories. So one observatory is in Antarctica, and what they did well, there's lots of observatories in Antarctica, but one of them in particular is they put light detectors on these strings in the ice. So it's in the ice, in a cubic kilometer of ice in Antarctica. The ice is remarkably clear, and they put little things that detect light in the ice. And this sort of observatory is to detect neutrinos, which are different from light. We have one just to the south of here, which is that way, or more southeast, in Washington State, that actually detects the distortion of space-time. That's a gravitational wave observatory, which is maybe, in a certain sense, that's like the least obvious thing to someone standing on Earth, if you imagine, that just by sort of looking at little discrepancies in what we observed about our solar system and the properties of light, 100 years ago, Einstein made a prediction that space-time was dynamic and that you could excite waves just in the actual fabric of space-time, of our universe. And 100 years later, we actually measured them. So actually, if you think about, Star Trek, and we're going in the warp bubble and blah, 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 that all is based on manipulating space-time, those ideas at least, whether one will ever actually do that. But we as humans, just in the last year, actually first measured those distortions of space-time. We've not yet manipulated space-time, but we actually can see what's going on in space-time for the first time, rather than just infer it from observations, other observations. So now we can actually, among these observatories, we observe neutrinos, we observe photons of different energies, we observe other particles that come from space, and we also observe the very distortion of space-time itself. Those are our different types of observatories that we have. Now, when we make observations, you might have heard, I remember in high school, they talked about laws of nature. There's laws, and you can't break the laws of physics, someone said, right? But what does a law mean? And can you break the law? I guess you can, but basically the word law is in science, it's used in several different ways. So when you hear the word law, sometimes a law is the first step. That first step, an observation, can be called a law. And this is one famous law that came out around Galileo's time, was that the planets orbit in ellipses with the sun at one focus. Now, what Kepler had done was he watched how the planets were moving around the sky, and he realized this was a good description of what he saw. So that's a law. That's one type of law. On the other hand, a law can be an explanation of the observation. So we have Newton's law of gravitation, which we'll talk a lot about that, and we'll talk more about it next week. And this is just written as a sentence, right? So the force of gravity decreases with the reciprocal of the distance squared and increases in proportion to the product of the masses. I can write it as an equation if we want it. This law is an explanation, it turns out. There's nothing in there about planets at all. And this also makes a prediction. This is true for any two objects in the universe, right? So this is another type of law, and it turns out that this law that I just put there, is the basic thing that makes the universe go. So on Earth, we kind of worry about gravity like we don't want to fall off a bridge. It would hurt that we worry about gravity. In that respect, gravity is very convenient because if I put something down, and it'll stay there. Down, gravity is useful for defining down. But otherwise, we don't worry so much about gravity. It isn't particularly dynamic. Which way is the gravity pointing? Down. It always is pointing down. But in the universe, gravity is what drives essentially everything. The evolution of a star is a star fighting against the possible, inevitable victory of gravity against trying to pull it together. Galaxies, the evolution of the universe as a whole, all have to do with gravity. So what is astronomy in a basic way? It's the science of things going on beyond the Earth, right? So anything beyond the Earth, we call that astronomy. Why do we exclude the Earth? Well, we have to leave things for other people to do, right? There's other sorts of scientists, but technically, the Earth is in space too. So if we were an astronomer on another planet, we would also include Earth in our studies of astronomy. So part of astronomy is indeed studying other planets, and we have other planets in our solar system, and it's fine for astronomers to talk about them, just we don't talk that much about the Earth itself, except when we want to, right? One key thing is we're going to use quantitative reasoning. So beyond, like that Newton's law of gravitation, and even Kepler's law that I talked about, the ellipse, that was a mathematical statement, both of those. So we will have to use mathematics, okay, and equations. So we often use quantitative reasoning in our everyday life. So here's a choice, right? Do I pick the bottles or the cans? Right? So we could make a judgment, right? So let's say you're optimizing, I want more beer. So I would pick what? The can. Now so that would be a quantitative reasoning. You could be like, I like drinking beer out of a bottle. There's some people like that, right? They like drinking beer out of a bottle. So you would always go for the bottle at the expense of getting less beer. But we could do something more complicated like this one, where we have three choices, and there's all sorts of different things going on. We could have 15 cans for $22, or 8 cans for $12, or 12 bottles for $18.80. And the point is, like, which would you choose? Hopefully, you don't choose Vancouver Islander lager, but that's besides the point. But what you would do, like how would you figure out what you wanted, right? So let's say you're having a big party with people that they don't really care what they're drinking, hence this, and they don't care whether it's in a glass or a can. So what would you calculate to figure out what was the best choice? You guys probably almost do this instinctively. Or you might not be able to explain what you do. But what would you do? Which would be the best choice for your party? No, you don't have to tell me the answer. The answer doesn't matter so much because no one's going to buy this junk. But the point is how would you figure it out? Can someone tell me? We could figure it out later if we wanted to. Why not you? What would you do? What's the thing that you want? Huh?
I'd use a calculator.
I don't mean like what? Oh, I have a calculator. What are you going to say? Calculator.
Oh, yeah.
Tell me, should I buy this, or this? No. What do you put in the calculator is the question. What would you do? What sort of math would you have the calculator do?
Division.
Division of what?
I have no idea.
Oh, come on. I don't need to know the numbers. But what would you do? You want to divide two things. So what two things are you dividing? What are the only two things you can divide?
The number of beers by the amount of beer in each one? Or like how many total?
Okay, so the number of beers divided into what? What would be the other thing? Like, what do you want to maximize? Like, let's say you have $100. How would you get the most beer with your $100?
The most volume?
You want to get the most volume of beer for your
Money.
money. Okay, good. So what are the numbers? Let's look at that can, the bottom one. We have, it even says volume, and it says next to it price, which is another word for money. It's like explained it to you. So you just go, I want most volume for money. So I go 15 times 355 divided by 22. That's one of them. I don't know what the answer is. The other one would be 8 times 355 divided by 12. And we would pick the one which had the largest number. Most beer per money. Right? Now, first of all, just to tell you, this was like, I said, like, we're going to multiply one-digit numbers and add things. This is harder than what I'm going to ask you to do, right? So and we'll do some examples. But of course, you'll get to use your calculator, like this gentleman did. But the calculator can't. You have to tell the calculator what to do. Even the Siri, you go, Siri, what should I buy? She would say, I don't know, or you should like consult. I have some, local AA meeting that you should talk to. I don't know what she would say. She's annoying. I mean, she's in here. All right, so what I'm going to do now is we're going to try to do an experiment, and that's astronomical, not beer, and we're going to measure something, but it's going to be, we'll see that we get a very big number. So what I have here is I need some volunteers, maybe 2 or 3, who are going to, and it's lovely because today is rainy and really yucky. So what you're volunteering to do is to experience being in the sun again. Now we're like in the absolute, we're actually in the time of year that the earth is closest to the sun, believe it or not, is right now. But what good does it do when the sun is only up for like 5 minutes a day? But we're closer to the sun now than at any other time of year, but it doesn't feel very warm because it's winter time. So what we're going to do is, who's going to volunteer? You won't burn yourself. I might embarrass you and like make a little joke, but I have this guy who just wants to be embarrassed. He's already volunteered. Come on down. It's not very, it's actually something pretty simple. So what I have here is a light, and I have some illegal light bulbs. So this has an LED in it, which is entirely useless for this experiment because it doesn't generate much heat. So we're going to take that out. So what wattage are those light bulbs?
40.
It says 40. So what we're going to do is actually today we're going to measure, if I don't electrocute myself or you, we're going to measure the wattage of the sun. We're like, how do you do that with a light bulb? Well, we're going to make an observation using our light bulb. So this light bulb has a power on it, which is 40, right? 40 watts. And we're going to figure out, that feels warm. Okay, so what we're going to do is figure out, by doing some measurements with this light bulb, believe it or not, how much power the sun puts out. Now, I was supposed to kind of, I had the webcam on so we record it, but I pointed the computer the other way, whatever. Now, what we're going to do is I have a ruler, and I want each of our volunteers to imagine how it feels to have the sun on their skin, like how warm it feels, okay? And maybe you want to close your eyes. What I want you to do is you move your hand up to this light bulb until it feels like it's in the sun, right at the closest place. And I'm going to measure how far away it is. Look, they're going to hold hands. So about there, we think, right? So this guy is about 5.5 centimeters, and about the same for him. I think they just like being close to each other. But the point is they both got about the same distance, about 5.5 centimeters. So we'll try. I'm about the same, right? If anyone else wants to experience the sun, I'll keep it here. Really you can nice. Come up. It is nice. What I love is like this new building over there, that alumni center. Sometimes you can stand in a particular place when the sun is out, and you can get hit by the sun in 3 different ways. Have you ever done that? You just stand there. So you get the sun coming for real, and then it reflects off, the building is shaped like this, right? So you get 2 reflections of the sun on you from the other side, and it almost feels like you're in I don't know, like in Seattle or something, like really warm. No, it actually feels quite a bit nice. All right, so let's try to do this. So I'm going to put this up here. I don't know if we'll be able to, I'll be able to record the calculation, but you guys are here, so you're not missing it. So what we got here was, what was it? 5.5 centimeters, was the distance it felt like the sun. Right? Something like that. And what was the other thing about the light bulb? You guys can go down now. Give them a congratulations. Excellent. Excellent. I don't know what other fun things we're going to do. Yes?
40 watts.
40 watts was the other piece of information. All right. Now, what did it mean to feel like the sun? What do you think it meant when we say it felt like the sun? Like in terms of, what did it mean, you think? A certain level of warmth, which meant that there was a certain amount of energy hitting your hand every second. So the energy hitting their hand every second at that distance was like the sun. So, okay, so we have two equations. We can write an equation. Power on the hand, so power per hand in some sense, of the light bulb equals power on the hand for the sun. And in astronomy, we use these astrological symbols, believe it or not, because astronomy came from astrology. So the sun is a circle with a dot in it. Okay, so, all right. Now, are you feeling the warmth from here?
No.
Not really, right? So what's happening? Why don't you feel the warmth?
Distance?
You're further away from the light bulb. So what's important is not just that the light bulb is 40 watts, but how far away you are from the light bulb, right? So she's further away from the light bulb. The sun is further away from us than the light bulb too. So we have to think about the warmth that we feel depends on the power of the object, which is 40 watts, and our distance from the object. Right? Does that make sense? Now, how does that work? Do you think the power goes down with just the distance, or does it go down faster? Does anyone have a sense of that? Well, let's think about it like geometrically, right? So this thing is putting out some amount of power, and it comes to a sphere this big. So when I'm this close, that power is spread out over a sphere this big, and it feels nice, right? Now, if I make the sphere twice as big in radius, how does the area of it change? Does it go, is it twice the area, or is it something else? Think about it. A bigger ball, or a bigger ball, does the area, let's say I make the ball twice as big, does the area of the surface of the ball double or do something else? You guys should know. Just, or think about it. Huh? It goes as the square. See, she put a pi in it. We don't need the pi. But you got the idea, right? As the ball gets bigger, the volume of the ball goes up 3 times, the cube. The area goes up as the square. So that's important, right? So, and that's why we have to know about doing exponentials and stuff. I unplugged my computer, and that's why, because I wanted you guys to feel the warmth for longer, but then we lost the screen, which means I've also lost the recording, but hopefully it'll come back. Okay. All right. So, if we want to think about it, over here we have the power of the sun, and we have how it feels on our hand, and those two are equal to each other. So what we're going to do is we want to work with this equation to figure out how much power the sun has. So, the first thing is on this side, that's for our hand, so it's 40 watts. And if you remember, the area over which that power is spread out goes as the distance away from the light bulb squared. So what was the distance? Do you guys remember? 5.5 centimeters. Now on the other side, we want to find out the power of the sun. Okay? So we're going to, we call power in astronomy, we call it luminosity, because everything is light. Luminosity sounds fancier than just power, so I write an L there. Now over here, I have to put in some distance. What distance should I put there? Do I put 5 centimeters? The distance between the Earth and the sun.
You want it in meters?
I want it in meters or in centimeters if I want. That'll make the math really easy if they're both in centimeters. So we'll figure that out in a second. But the key is I need to know the distance to the sun to figure out anything physical about the sun. So that's why measuring distances in astronomy is key. And we can't run a measuring tape out to the sun. Although we can send a beam of light to the sun or near the sun and bounce it back. So we know the distance to the sun very accurately. And we don't need to know it very accurately for this, but it's 150 million kilometers. So I've written this in a tricky way, which I'm going to explain to you more in detail. I've written it in scientific notation. So I've written 150 times 10 to the 6, and it's all squared, right? So this means I don't have to write a lot of digits. If I were to write it out, it would be 150 like that, right? Which is awkward to write all those zeros. I could forget one, and I'd be off by a large amount. I'd be off by 10. Now, we have kilometers here and we have centimeters there. Usually in this class we'll do everything in centimeters because that's just how we do it. So you can write it down or it'll be on your exam. What is the distance to the sun in centimeters? So you won't have to worry about doing these conversions so much, but in centimeters it's even worse. It's 10 to the 11 centimeters, which would be another 5 zeros on there, which makes, that's awkward. So now let's see what we have here. We know this, we know this, we know this, and this is the power of the sun. That's all. There's only one missing quantity here, so we can figure it out. And all we do is we move this thing over here. Okay. So, do people see what I sort of did there? I just moved that over there, and I could put them both underneath here together. So now we do have to calculate something. We have to calculate this number here. So we have 150 divided by, why don't we make it just 150 divided by 5? Because I like that. That's kind of a round number. We'll do that. So 150 divided by 5 is what? Does anyone know? How many times does 5 go into 150? How many times does 5 go into 30? Oh, sorry, that's the answer. How many times does 5 go into 15? 3, I told you. So 5 goes into 150 30 times. So we have 30 times 10 to the 11 times 40 watts is the luminosity of the sun. So 30 times 10 to 11. So here's the trick. We have this square. So what that means is everything in there, I have to multiply it by itself. Now, like I said, I don't want to multiply two-digit numbers. So what I'm going to do is I can make this 3 times 10 to the 12. I just moved that 0 over there. So now what I'm left with is 3 times 3. What is 3 times 3? 9. Okay, good. Whew, I didn't know whether you were going to do with that. Okay, 9. Okay. Now, what's 10 to the 12 times 10 to the 12? I said you wouldn't have to multiply numbers that were more than one digit. And this is 13 digits. So I've cheated you. But no, so how do I do it?
10 to the 24.
10 to the 24. So when I do this, all I have to do is I take the 2, a one-digit number, and multiply it by 12, which it's a two-digit number, but not a big one. So I have 10 to the 24 times my 40 watts, which is, whoa, do you think I'm going to get it? Do you think it's going to be close? I don't know. So we get 36 times 10 to the 25 watts, right? Because I have an extra 0 here. So 3.6 times 10 to the 26 watts is the luminosity of the sun from our friends here in the room. So does anyone, there's someone with a computer there? Can you type in? See, he doesn't even know I'm talking about him right now. So I'll go up and ask him. Hey, yeah, you. So can you type in your Google and type luminosity of the sun? And see what you get.
Let's see.
Oh my goodness, what does it say?
3.8 times 10 to the 26 watts.
And what did we get with these two jokers here? This is 3.6. The real answer is 3.8. 10 to the 26. So they were off by, I don't know, something. Less than 10%. Okay? With this light bulb. So that's what the sun is doing, right? So it's a really, really, really huge light bulb. So if we do that in watts, I have to go 3, then I have to go 26. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and then put in the commas maybe. They're really annoying. Maybe there's one there, one there, one there, one there, one there. Oh, maybe that's right. Okay, that's the wattage of the sun. So you can see it's awkward. This is a lot better. We can just write 26 here. And that's why the sun has to be so big, because they have to write that number on the sun, right? It takes a lot of space. But you can see, okay, so with a very simple idea, with you telling me what to do, right? She said, oh, the further away it spreads out like the square, right? We needed one piece of information that we couldn't get from the room, which is the distance to the sun, right? But with that, we can figure out the luminosity of the sun, the power of the sun. And this power is huge. And it took people saw, oh, there's the sun, it's really warm. They didn't know how far away it was, but maybe they did measurements like with the transit of Venus. I don't know if you guys remember that. You could figure out the distance to the sun accurately in meters or centimeters. And they realized the sun is really, really powerful. And we have to understand that it took a lot of smart people a long, long time making mistakes to figure out where this power comes from. But we now know where it comes from. So let's go back here. So we can skip that. Okay. So when we have an equation, what we have, I had 3 previous examples. I didn't give you 3 previous. No, I actually did I gave you the beer example, too. So you have an equation in mind. So the equation is something equals something. In our case, our friends came down. My hand feels like it does on a sunny day. That's like. That's the same as equals as far as astronomy is concerned. We often don't, we're stuck here on the earth and we're trying to understand on the other side of the universe. Often we don't worry about, is it really precisely equal? I'm not going to worry about that. I'm already doing a good job. So we have an equation. And you can think of an equation like a recipe. They have different ingredients that you need to put into the recipe. The power of the sun, the distance to the sun, for example. And you have steps to follow. And those steps to follow are given by the mathematical expression of drawing the line. It meant this divided by that times itself. And that's the steps of the recipe. And you make something new. I made this thing. I didn't start with it, but I make something new. But I can use it any way I want. If I were to give you 3 of those 4 numbers, like if I were nuts and said, oh, guys, I don't know the power of the light bulb, but we knew the luminosity of the sun, right? I could have done it that way, right? Let's say I threw out this little box and I needed to figure this out. We could have done the same experiment today. Oh, how warm does it feel? It feels like the sun. Dude, look up the power of the sun. And then we figure out the power of the light bulb. Now that would have been really boring. But we could have done it. So you can, unlike a recipe, I can use equations different ways. I can give you pancakes and come back with flour, eggs, and milk. Right? In equations, you can do that. In real life, it doesn't work so well. So what we're going to do is, well, you could uncook the product to get at some of the ingredients. And the equations we use involve multiplication, division, and powers usually, not addition. So we're going to go through a bunch of strategies like the ones we use today, but in more detail of how to deal with these big numbers efficiently.
Or getting used to the fact that we will be doing equations in this class. There won't be a lot of it, but we want you to be able to figure things out using numbers. For example, like I don't know if anyone's actually bothered to look at the final exam that we put up there. But just to give you an idea of what that's going to be like is, for example, on the board we did this calculation using scientific notation, and on the exam you won't have something like that really. There will be problems where it's multiple choice, and you'll have different choices, and you will have had to do a calculation that might involve scientific notation. And there might only be 1 or 2 questions like that. On your tutorials and other things that you do, there will be those sorts of questions with the scientific notation. And we're going to use it a lot in the class. So I want to go through it, but if it's not fully sinking in your head how you're going to use it yourself, don't worry about it so much. Because you'll, even if you were not to get it right on the exams, the 2 exams, we're talking between the 2, it might be a point. Meaning a point off your final mark if you don't completely get how scientific notation works. Okay, so that's what we're going to start doing now with some examples of just going through the rules. Here's another question that we might want to ask, and we'll use some scientific notation to do that. How fast does the Earth travel in its orbit around the Sun? So the first thing we have to do is, what is the equation that we would use to figure out how fast it's going? So what are the 2 ingredients that we need, and well, we want to find speed, or we would like to relate time elapsed to distance traveled and speed. So how are those 3 things related? Does anyone know from your experience or from a class? Yes. Speed is distance over time. Or you could imagine time times speed is distance would be another way of looking at it. These are the equations we're going to use a lot. There are going to be some that are more complicated and less familiar, but basically we have speed or velocity is distance divided by time. What are we doing? So what ingredients do we need, right? So if we want to calculate the speed, we need to know the distance and we need to know the time. So how can we figure out those things? So how would we get, what would be for the Earth going around the Sun, what would be a natural time to think about? The time elapsed, right? Does it make sense to think about how far the Earth moves in a day? Is that something that people know offhand? Probably not. But what do we know? Well, what's the Earth? Yeah. A year, right? So we can think of the time on the bottom would be 1 year. But what's the distance over a year? Well, let's think about it. What does the Earth do in a year? Come on, it's the easy answer. Just say it. Don't be afraid. Not you. It's your answer. What does the Earth do in a year? It goes around the Sun. That's all. So what does going around mean? It went in a circle, more or less, circles around. And so the distance is the length going around a circle. And that's the Earth going around the Sun. So what would that distance be? Here we're going to have to put in, remember, right? So what's the distance going around a circle? It's the diameter times something else, like this. Pi, times pi, that's what it is. So what I'm going to do is I'm going to write twice the diameter, twice pi times the radius. I'm going to leave the pi there because it turns out it'll cancel out. I'd rather not do the math with the 3.1415 blah, blah, blah. Okay, so what's this thing, the radius that we would use? We talked about it last time. It's just the distance between the Earth and the Sun, or the average distance, right? So we talked about last time, it's 150 million kilometers. I'm going to write it in kilometers, because that'll give us velocity in kilometers per time. Now, is it interesting to think about a velocity per year? Not really, right? We'd like to think about it per hour, or in astronomy, per second, right? Because things go pretty fast in astronomy. So what we have to do is think about how many seconds are there in a year. Right? This is where, like, in my head, I have a little number. You can calculate it if you want for yourself. But there's about 3.15 times 10 to the 7 seconds in a year. I just know that because it's very easy for me to remember. Why is it easy? Because it's pi, more or less, times 10 to the 7. But how would you figure that out if you wanted to know it? You have to think there's 24 hours in a day, there's 365 days per year, and there's 3,600 seconds in an hour. So you'd have to multiply that all out, you get a number like this. So we can see, again, we're using the scientific notation. We can figure out about how fast the Earth is going around the sun. And that's why I like having this pi here, because the pi cancels out that pi. And we have 150 million kilometers, and we'll turn that into the same thing with the scientific notation. So I have 1.5 times 10 to the 8 kilometers divided by 10 to the 7 seconds. And I can just go 2 times 1.5 is 3. 8 minus 7 is 1. So just by you doing absolutely nothing, every second you've gone 30 kilometers. That's how fast the Earth is going around the sun. And that is, if we think about other velocities, how fast the sun is moving relative to stars near to the sun, it's also a number like that. How fast the sun is moving around the galaxy is about 200 kilometers per second. So that's really fast as far as we're concerned, right? So anyone have an idea of how fast if you take a jet plane, meaning not a fighter jet or anything like that, but you're on the jet plane and you're flying somewhere far away. Do you know about how fast that goes? Anybody? It goes about 1,000 kilometers an hour. That's a nice number to keep in your head, which is 1/3 a kilometer per second. So the Earth goes around the sun 100 times faster than an airplane goes around on the Earth. Okay, so it's really fast compared to what we're used to. Okay, does that make sense so far? Okay. But again, we just used our ingredients here of, I'm just doing this mainly as so you have an idea of how fast things move in astronomy, but also so you see another example of how to do the scientific notation. Okay, so how would we write that number in scientific notation? I just want people to shout out A, B, C, D, or E. So I'm going to count to 3, and then just say what you think the right answer is, and I'll try to accumulate all your votes. So 1, 2, 3. Wow, that was like a chorus. Almost everyone said D. Okay, well that's good. Right, so all those things there, except for the second one, are correct ways of writing that number. It's just when we think about scientific notation, which also makes the math easier, is you make the number in front between 1 and 10. So technically, this is not scientific notation, because I wrote 150 here, right? Scientific notation, this thing I want between 1 and 10. And the reason I want it between 1 and 10 is I usually will throw away the extra digits, and then I'm just multiplying one-digit numbers. It's to make your life easy. Now, why did I write it like that to start is because how I remember it. I don't remember, it's hard to remember. 1.5 times 10 to the 8. It's much easier to remember 150 million. That's like how much it would be nice to have in my bank account. It's not too much, it's not too little either, it's comfortable. But, yeah, no one, you're under everyone's radar at 150 million. Like, no one expects you to do it. But scientific notation technically is always like that. So between 1 and 10 and times 10 to the something. So just to go through the math, I think most of you understand this, I think, but I'm just still going to do it just to get everyone on board. So the better way of how we put together the scientific notation, the basic idea is you write whatever it is where we have all of the zeros, I can keep track of the numbers of times that I would multiply 10 by itself to get the numbers. So here we have 1,000,000, which is 10 times itself, 10 times 10 times 10 times 10 times 10, 6 times. And the way we write that is I just count the number of times and I write that as 10 to the 6. Now the reason that this makes, we still have to do the small numbers. Again here, when you write numbers less than 1, or between 1 and 0, you usually don't write commas. Here I've written them with a space to help us count. And this one we can think of as 0.1 times 0.1 times 0.1 times 0.1, and it's 7 times, it turns out. And that's a tenth times itself 7 times, which is 1 over 10 to the 7, which we write as 10 to the minus 7. And once you have these definitions of how the scientific notation works, that lets you think about more complicated numbers like that guy, where we divide it up into the number between 1 and 10 and the rest. And I multiply those two together, so I have some number between 1 and 10, and I multiply it by 1,000,000, and I can write 1,000,000 as 10 to the 6. Right? But what makes this, I mean, it's convenient because we don't have to write all the zeros, but it's also useful because it makes things like multiplication a lot easier, maybe. So here we have this, we did a bunch of examples here, but here's one that's just 2,000,000 times 2,000,000, 2,000,000 times 200. And if you weren't careful, if you were to write it all out and leave out a 0, you could make a mistake. But here you just rearrange things, and you put the 2's together and the powers of 10 together, and then you can just multiply it all out by counting all the 10's, and you can see basically what you do is just add the exponents, which probably a lot of you already knew. So here's a division, right? So in division, it works the same way. You end up taking the things that are powers of 10 and separate them from the other parts, and then you just can write out all of the 10's, and you end up canceling ones on the bottom versus ones on the top, and you get 10 to the 6. So that's why things that are between 0 and 1, things that are smaller than 1, work out to have negative exponents, because that makes sense in how we would do this. So we would go 8 minus 2 is 6. 4 divided by 2 is 2. So that's how come we can avoid doing lots of crazy multiplication. Now, if you end up with some 10's downstairs at the end, then your exponent of your answer is negative. It's just the number of 10's in the lower portion. So the last bit that we have to think about is that's how we do multiplication and division. The other types of equations that we're going to use will have powers. So it's 10 to the 2 and then raised to the third power. And what that means mathematically is I've gone 10 to the 2 times 10 to the 2 times 10 to the 2, and I can write that all out in all the tens and count them, and I get 6. So the rule is, if we're doing powers, is we just multiply those two out. Now, of course, your calculator can do this, but if you have these rules in your head, you'll know the answer before you even get it into the calculator. And at least I find I often make a mistake when I type into the calculator. But sometimes, especially on the exam, when it's multiple choice, you're going to be given different answers that are much different from each other. They would have, the thing in exponent would be much different. It could be, one could be 10 to the 8, the other could be 10 to the 4. And just by thinking it through, you'll get the exponent right. And you know the answer, right? Because they're that different. On the other hand, when you're using the calculator, at least for me, I often get the exponent wrong. Because you have to remember, in fact, how to type the exponent into your calculator. Like, how do you do it? I can type a number and then there's like an EE button or something, but you can screw that up. Right? So it's very useful to be able to think these things through with pen and paper. So here's the basic rules, right? So we have 10 to the A times 10 to the B is 10 to the A what? A plus B, not AB, but A plus B. 10 to the A divided by 10 to the B is 10 to the, all right. And 10 to the A, and then raise that to the B is 10 to the AB. All right? And what if this one I didn't do? A over B is in the exponent. So, these things actually, we might design the problem so A divided by, like, A could be an even number and B 2. We can make it so it's easy. All right, so what is this thing in scientific notation? So let's just look at it, and we have a bunch of different choices. Now, a couple things to keep in mind. Some of them are quite different from the others. So that's my little lesson, that once you get out the calculator, you've already spent more time than to think it through. But if you've thought it through, just say the answer. I'm going to go 1, 2, 3, and then you'll all say the same thing, possibly. 1, 2, 3. Wow, look at that. That's better than clickers. It's cheaper, too. But I can't keep track that way. So it's A, right? Sometimes it's, we don't have really that many of these questions in here. Okay. So now we're shifting gears. So, did anyone already have the tutorial today? Good. So you know about this. Yes or no? You knew how to measure angles with your hands. I hope we taught you this. It was in the sheet. So this is just convenient for when you're out looking at things, and it's useful for the tutorial, right? So it's a little bit off. So that's 10 degrees. It's not 10 to the 0. We've just been doing scientific notation. But it turns out that the width of your fist is about 10 degrees. And if you go like this, like you stretch things out like that, that's about 20 degrees. And in the tutorial, you'll use this to measure angles, to measure the height of the clock tower, as I mentioned, and also the distance to the clock tower, without actually walking to the clock tower or climbing up it. Did anyone climb up it today? No, the TA didn't. I warned you against that. Now, let me see. Do we have other ones, other examples? It turns out like the width of your finger is about 1 degree. So one thing that you might want to try is, you think the sun is so big, you should be able to cover the sun with the tip of your finger, believe it or not. The sun is actually smaller than your fingertip. Now you might be like, oh, my hands are different from your hands are different from my hands. And how does this all work out? Turns out people who have longer arms typically have bigger hands. They're wider, right? So that's why this all works out fine. So if you have a smaller hand, usually your arm is a little bit shorter. If you have a long arm, your hand is typically a bit larger. But this already is telling you something, right? So the angle that we perceive something depends on the actual size of the object, my fingertip, and how far away it is. So the angles that we measure depend on the physical size of the object and the distance to that object. And we're going to use, that's how we manage to figure out distances of things without going there. Is again, it's another equation. The angle that something subtends depends on the size of the thing divided by the distance to the thing. So I want to talk about how we measure angles in astronomy. So the first thing is we have a degree, and most of you have already heard of a degree, I think. And a degree is defined that a circle has 360 degrees. Why did they use 360? Maybe you could think of some reasons. Can you think of a good reason? We talked about it at the beginning. A year has about 360 days in it. I mean, it's 365, but that isn't a coincidence, right? So the Earth, in its going around the sun, goes about a degree a day. As far as the ancient people, they didn't realize the Earth was going around the sun, at least not a lot of them did. What you would think is that the apparent position of the sun each day would move by about 1 degree. So that's why we have this definition. It isn't completely arbitrary. Why is it 360 instead of 365? The math is easier than 360. Imagine 365. Oh my goodness. So 360 means a quarter of a circle is 90. It's a number that's divisible by lots of other numbers. So that makes the math easy. Then we subdivide, right? So we want to think about angles smaller than a degree. Remember, your fingertip is about 1 degree across when you hold it at length, at the length of your arm. And I can perceive things that are much smaller than the width of my fingertip. My fingertip isn't, I can see wrinkles up there and whatnot. So with your eye, you can perceive, if you have normal vision, you can perceive things down to 1/60th of a degree. So we give a special name to 1/60th of a degree, that's an arc minute. And we divide the arc minute further, that's maybe you can see the pattern. Each arc minute consists of 60 arc seconds. So the ratios are the same, like seconds to minutes, minutes to hours, the same as for time. So we can think of really small angles in astronomy, and we will have to think of really small angles. So your eyes can resolve details bigger than half an arc minute, so 30 arc seconds. All right. And when we think of, if we use a telescope and look at a star, the star won't appear to be just a point of light. It'll look like a little blob. And the size of that blob is about an arc second, regardless of the star. So if you think about it, does that mean all stars are the same size? Remember, if the stars are different distances from each other, even if they're the same size, they'll appear different. Doesn't mean that they're the same size or the same distance. It's just because our atmosphere is wobbly, and it makes the image of the star not be its real size, but typically 1 arc second its size. Okay? So the nearest stars to us, if you think about it, if I'm on the Earth and here's the sun, I'm going around the sun each year. And if I look at a star, that star will appear to move due to my motion going around the sun. And typically, that's 1 arcsecond back and forth each year for the nearest stars. So that's where the arcsecond. This is just to give you a sense of the size of things. Whoops. So, how big, I gave this example about our hand and fingers. How big does an object appear at a given distance? And this question mathematically means, what angle does it subtend? So what angle does it appear on the sky? And normally, if you were to think about this, back in high school maybe, you would draw a triangle and you'd have to use sines and cosines. We're not going to do it that way because the angles in astronomy are typically quite small, so there's an easier way. So let's imagine that we're standing somewhere, that's us, and we're standing in the middle of a circle. And I have some object at a distance d away from me, and its length is L, and it's sitting out there. And I can see where it is, and I can imagine it also subtends some angle. And I've written that angle as alpha. That's in between us and them. I've just written it like that. So when I look at it, I can think of, well, that's a sort of like a piece of the circle I've drawn there. And the fraction of the circle that represents the angle, this part, this fraction of this circle on the inside, is the same as this compared to the big circle on the outside. So this fraction and this fraction are the same. So we can write that as an equation, right? So the fraction of that length over the entire trip around the circle is the length divided by the circumference of the circle, which is 2 pi times the radius of the circle, which here is called d, okay? On the other hand, the little angle, any angle we have, is some fraction of a circle, and that fraction is the angle divided by 360 degrees. That makes sense? So again, we have an equation, and we came up with this equation by drawing these two circles. So that gives me a relationship between the angle something takes up versus its length and its distance away. And if we do the math, you find that the angle is 57 degrees, but you can remember it as 60 if you want, times the length of the object divided by the distance. So let's think about what this means. So an object that is physically bigger at a given distance will appear larger. It'll have a larger angle. On the other hand, if I take something of a given size and I move it further and further away, it appears smaller and smaller and smaller. This is something probably all of you have in your everyday experience. You understand it, right? But now you have an equation for it, the precise relationship between these different quantities. So, for example, if I think about my fingertip is subtends 1 degree, essentially what that means is the length between my eye and my fingertip is 60 times the width of my fingertip. And we could measure that if we wanted to. So what that means is from here to here is about, my fingertips maybe 1 centimeter across for my little baby finger. This is about 60 centimeters, more or less. So that's what's happening there. So and that's just the reason why this works out to 20 degrees is because this length is about 3 times, 1, 2, 3, up to my eye, more or less. You could try it. So 20 degrees, 1, 2, 3. So we have, well, I don't know that. Maybe I'm over-explaining it. But we can use this now to do a whole bunch of things. So typically, you can think about distances in astronomy, and they'll get really, really big. They go up by factors of 10 very quickly. So how far are you from someone in the neighboring seat? You are typically how far apart from each other? You two. What would you call that distance? About. Round number. It's a meter. That's all I'm looking for. It's a meter. You're 1 meter apart, more or less. Right? That's our everyday, or a few dozen centimeters for those of you who are closer, but typically a meter. How far are we from the board? A few meters, right? That's the scale of our room. If we think about how far we are from downtown Vancouver, that's a few kilometers, right? It's going to get big pretty fast. How far are we from the sun? So that's the next step, like we're leaving Earth. This is a few 100 million kilometers, a couple 100 million kilometers. Now we're going to take a big jump, right? So this is the scale of what we've explored as humans and the robots that we send out. But how far are we from the nearest star is where things go a little bit crazy, right? Tens of trillions of kilometers. So it's another factor of a million almost compared. So the distance between Earth and the Sun is about 300,000, or maybe think about it the opposite way. The nearest star is about 500,000 times further from Earth than the Sun is. The nearest star after the Sun. Does that make sense? So the stars are really, really far apart from each other. How far are we from the nearest big galaxy? We're in a galaxy, so I'm thinking about the other galaxy, the nearest big one. Now we're numbers like quintillion. So unless you play games like Cookie Clicker, you've never encountered quintillion in your life. Has anyone played that silly Cookie Clicker game? No. It has numbers like, kids playing, and they're like, what's a quadrillion? What's a quintillion? Because they'll never have seen it. But the nearest big galaxy is about 10 quintillion kilometers away. And then finally, the distance of the entire size of the universe that we can observe, you can see that's only about 1,000 times larger than the distance to the nearest galaxy. So the big jump in scale, it turns out, is the distance between individual stars. But then if you think about the distances between galaxies, it's not big compared to the size of galaxies. And we'll learn a lot about that as we go. Right. So just to introduce things, because we're going to do an exercise, is how do we measure distances in astronomy? And you see all of these examples, and we'll understand them all as the course progresses. But right now, we're looking right in this corner down here. So how do we measure distances? First, in the solar system. So in the solar system, we can send radio waves and just bounce them off objects. For example, we bounce them off Venus, and that will tell us the distance to Venus very accurately. We can bounce them off the moon. So we know the distance to the moon, we know the distance to Venus, we know distances around the solar system very precisely now, because we just bounce light waves off them. So that's the first step in our distance ladder. And that tells us what is the distance between the Earth and the Sun, which is this number. But we know it more precisely than I've written it there. And that number, the distance between the Earth and the Sun, we use to start measuring the distances to the stars. We don't go to the stars. We don't bounce a radio wave off the star. But once we know the distance between the Earth and the Sun, we can figure out the distances to the stars by measuring angles. And this is how it works. So as the Earth goes around the Sun, that's down on the bottom corner, the bottom left corner of the plot. If we look at a star, what the star will appear to do in the sky is trace a little circle. And that's not because the star is moving, it's because I'm moving. So as I go around like this, if I look at someone nearby, they move a lot more as I move back and forth compared to someone further away. And we can figure out how, what the angle that they move by, how does that correspond to how far away they are from us? So imagine this is how you do surveying, for example. So we have some surveyors' equipment here, and they want to see how far it is across the stream, but they don't want to get wet. So what they can do is they set up 2 of these angle measuring telescopes, and they point them both at the tree. And what they can do is they can measure the angle, because the tree's, let's say, over there, so this telescope is pointed like this, and this is pointed like that. I'm pointing at that lectern thing. Now, if I turn that up, that's a triangle with an angle, right? It's not like this, it's like that. And you can figure out how far away the tree is in that way. So, if you're going to use trigonometry, and you've done this carefully, you'd get a tangent for how you would figure out that distance. But we're not going to do the trigonometry. We're just going to draw the circle diagram again. And here we're going to figure out the distance to the star. And one thing to keep in mind is we can't even in principle, well, we can in principle go to the star. It would just take a really long time. For us to bounce a light wave off a star and have it come back, it would take, even for the nearest star, it would take about 9 years. We can figure out how far the star is away just by staying here on our planet. And here's how it works. Again, we're thinking about that circle that we drew before, but here we are thinking about it in maybe a different way. We want to figure out the distance to the star. And let's imagine that there's 2 of us looking at the same object at the same time. And this is like looking at the tree across the river. So there's some distance between you and me, and that I call the baseline. So, and then there's the angle, which is the difference in the angle that I see versus the angle that you see, which I write as alpha. And again, the fraction that the baseline has of the full circle is equal to the fraction of the angle out of 360 degrees. So it's the exact same equation as before, except we have different numbers, and what we know and what we don't know are different. Here we want to find out the distance, so we solve for the distance, and we find that the distance is the baseline, again, times that 57 or 60 degrees, divided by that angle. Now that angle we call the parallax. We call that the parallax. And why do we call it parallax? Because parallax is the effect, like with your eyes, you have 2 eyes, and that lets you judge whether things are near or far away by measuring the angle of a given object from each of your eyes, and that's called parallax. For us, in astronomy, our baseline could be, if we want to measure the distance to the moon, for example, we could have 2 people looking at the moon on different places on Earth. Or if we want to do the stars, we wait for a year. But let's just see if we think about the moon. So we want to figure out how far away the moon is. And I have 2 people looking at the moon at the same time. They're 1,000 kilometers apart, maybe here versus in Alberta somewhere. And we both look at the moon at the same time, and we note down what stars we see around the moon. And we figure out that we have 9 degrees of parallax. So my friend in Alberta is looking in a direction 9 degrees away from where I'm looking. So how do we figure this out? Well, which recipe we use is just what we had here. We know the baseline and we know the parallax and we want to find out the distance. So there it is. What's the baseline? A what? 1,000 kilometers. And what's alpha? It's the only other thing I gave you. What? 9 arc minutes, right? So we have the right ingredients, except if you think about it, so we have the 2 ingredients, but this is not in degrees, is it? It's in arc minutes. So we're going to have to convert the arc minutes to degrees. Right? So I have 9 arc minutes is 0.15 degrees. And then I can just use the equation. Right? So I have 1,000 kilometers, and then I have to multiply that 57 divided by 0.15. If I use the number 60, that would just be 400. So it's just like 400. And we get 380,000 kilometers. We've not gone to the moon to do this. We just had to go to Alberta, right, which this time of year might be colder than the moon, but still, it's not all the way to the moon. So what we do to measure things further away, well, I don't know if you have time to do this. You only have 6 minutes. So let's give how we worked for the stars, and then we'll go back to the worksheet next time. So to do it to the stars, like I said, we look at the same object 6 months later. And if you think about it, we move in 6 months, we move by 2 astronomical units. We move not 1,000 kilometers, not 100,000 kilometers. We move 300 million kilometers without doing anything. We just have to wait, right? Because we've moved from one side of the Earth's orbit to the other. So as we move from one side of the Earth's orbit to the other, we can look at the same object, in this example, the Pleiades cluster, and see where it appears in the sky at those different times of year. Now, in reality, these shifts are really small and really subtle. The stars in the Pleiades will only shift by about 100th of an arc second. It's not like you have any confusion, like it doesn't move over there. You're measuring very precisely what's going on. Now, what we define things, it turns out, is the parallax angle isn't the full amount that it shifts, it is half. Right? The parallax angle is 1/2 of this full shift. So let's think about it. What's the baseline in this case? What's this baseline over this angle? What would it be in kilometers? What? 150 million, right? Or the distance just between the Earth and the Sun. So we call that an astronomical unit. And then the angle is this one, and that's what we measure. And then we can figure out the distance. And to do this, we use the Earth's orbit as a baseline, and we do this all the time. So we make up a distance unit for it. So if the baseline is 1 AU, and the angle, the parallactic angle, is 1 arc second, we say the distance is 1 parsec. 1 parsec. So that's the distance that we use in astronomy. And that makes the math, we do that to make the math easy for us. So if we measure the parallactic angle, let's say, just for argument's sake, it's 1 milliarcsecond. What would the distance be? It would be the angle is 1,000th of an arc second. So the distance is 1,000 parsecs, or kiloparsecs. So this is a quite simple formula now, right? Because the baseline is gone, because we're always in astronomy, we're using the same baseline. It's the distance between the Earth and the Sun. It's always the same. And the distance that we want to use is, we give it a unit called parsec. So for example, let's say we were on Mars instead of on Earth. Would the parallax angle be larger or smaller on Mars than on Earth? Think about it. Is Mars, what would be different on Mars than on Earth? Anyone know? Pardon? The baseline. So is the baseline, what is the baseline on Mars? It's the, I don't need the number, but it's the, huh? The distance between Mars and the Sun. So that distance is larger. So if you're on Mars, the stars will appear to move a bit more than on Earth. If you're on Jupiter, they'll move 5 times more than they on Earth. On Saturn, 8 times more. But since we're on Earth, we always use this formula. So I don't know if we... So how big is a parsec? Again, we can use the same formula. Our baseline is 1 astronomical unit now, and our angle is 1 arcsecond. So we're using the same formula again, and we're going to try to figure out how big is a parsec in kilometers. And I think you can already see it's going to be a big number, because the baseline is a big number, and this arcsecond is really small compared to 57. So we have to convert the arcseconds to degrees. There's 60 arcseconds in an arc minute, 60 arc minutes in a degree. So we end up with this formula where we have it in degrees. So we have 57 degrees, and we multiply everything out, and we get 3 times 10 to the 13 kilometers, or 30 trillion kilometers is 1 parsec. And the nearest stars are just more than a parsec away, maybe 1 1/4, 1.5 parsecs.